Hello everyone. So we are going with the next arithmetic instruction, that is multiply. So in multiplication, the instruction will be like this: mul p l. So if we have a quick recap, we have in addition or subtraction or ADC or SBB increment, all these things upon two different operands. That is, if I say an instruction written in to add two registers, the addition will be something like add BL comma CL. But here in multiplication, we have only one register. So what is this signifying? If am I going to multiply only one value with the same value? No, we cannot multiply it. So there is some significance saying that if you go back to 8085, see all the operations are or performed with the help of accumulator. But in 8086 there was some relaxation saying that this is like add, ADC, SB, SUB, SBB and some other instructions like increment, decrement. All these instructions doesn't require an accumulator. They can be they can be performed upon two different registers also. So, but for some complex instructions like multiplication, division are done on accumulator. So before going into the brief explanation about the multiplication instruction, first of all we'll have a look at what are the different accumulators. There are three different accumulators in 8086. They are 8-bit accumulator, that is AL register. It is only AL register. It cannot be AH also. And 16-bit accumulator, which is AX register, and 32-bit accumulator, that is DX and AX, where lower word is stored in AX register and higher word is stored in DX register. So generally we have two different types of multiplication. What are the two different types of multiplication? That is 8-bit multiplication and 16-bit multiplication. So now we will go with the exact example of mul BL. So what does this say? Now in this particular one, the moment I give mul BL, BL is of what size? BL is 8-bit register. So the 8-bit accumulator, it will be multiplied with the 8-bit accumulator, that is AL into BL, and the result will be stored in AX register. So why I am saying it is AX? Because now I'm not doing addition over here, but I am doing multiplication. So 8 bits value gives me 2 power 8 values. So 8-bit, that is 2 power 8 values into 8-bit, that implies 2 power 8 into 2 power 8 gives me 2 power 16 different values. So it cannot overcome the size of 16 bits. So at a maximum, if I multiply 8-bit into 8-bit, the size is 16-bit itself. So in a worst case scenario, and I'll take an example to explain this one. Worst case scenario, where AL has FFH and BL has FF. These are the large values which an accumulator, 8-bit accumulator can have. That is FF into FF. So if I multiply these two things, it is F into F. So F value is 15 into 15, which is equal to 225. So 225 divided by 16 gives me 14 and 224. That is, the remainder is 1. So exactly, this is the remainder will be placed over here, multiplication. So what is the 14? It is E. 14 is equivalent to E. Therefore now after this it is 15 into 15, again 225 plus E 14. So what I am getting, 239. So 239 divided by 16. So it is 16. So it will be 79, 64. 1 and 4. Again, what is the value that I am getting? Here it is 15 and 1. So 15 is equal to F. The remaining value which is there is 14. 14 is equivalent to 14 is equivalent to E. Therefore, I placed over here. So if I'm sorry, E, A, F, E. So this is FF into F. So the same value will also be there if I multiply again with F. So it is EF1. So it is 1. So F plus 1, 15 plus 1 will be 0 because it will be 10. So it will be 1. So 15 plus 15, it will be 30. If I divide by 16, so it will be 16 one time. So it will be 14. So what is the value of 14 is the, so I'll be getting E. So the remaining 1. So E plus 1 will be F. So if I multiply FF into FF, the largest values available, I'm getting the value which is equal to FE01, which is a 16-bit number. So from this one we can easily identify that the maximum value, if I am multiplying two largest values, I am getting the maximum number to be 16-bit number. So now I'll take one more example saying that if I say mul BH, what will happen? It is BH is an 8-bit register. So what it will be doing? It will be saying whether it is AL or H. It is AL. Good. AL into BH because the accumulator is fixed. It will not be changed. 8-bit accumulator is always AL and the result will be stored in AX because AX is also a fixed value. Clear? So if I do one more, if I go do 16-bit multiplication, that is example I'm taking mul bx. Now if I do mul bx, what it will be doing? It will be taking ax into bx and the result will be stored in dx and ax, where lower word will be stored in ax and higher word will be stored in dx. That's it. So this is all about the multiplication. Now the second next instruction is integer multiplication. Integer multiplication. So we are very clear about, we know what is integer. So integer is something called 0, 1, 2, 3, 4 and so on. There is other side -1, -2, -3. These are called integers. So integer here, multiplication of signed numbers are done with an instruction called mul, but uh, for unsigned number, signed numbers or unsigned numbers, we use mul operation. That is, for unsigned numbers, we use mul instruction. For signed numbers, we use imul. So, for signed numbers. So here we are not having like in addition or in a subtraction or in increment or in decrement. We know that it is a two's complement form, so we made it very easy. That is, whether it is a signed as well as unsigned numbers, it can be done. But in the multiplication, we use two different algorithms for multiplying a signed number and an unsigned number. For unsigned number, for unsigned multiplication, we use conventional method. We use conventional method of multiplication. But for signed multiplication, we use Booth's algorithm. If you go through the computer architecture and organizations, it will be available with the Booth's algorithm. But to explain about this one, this particular point is irrelevant. Just remember that if I have a signed number, we have to use imul rather than the mul operations. This is important for us. So if a question is asked, first try to figure out what is the answer which I have been, what is the question that I have been asked. So either it is a signed multiplication or unsigned multiplication. Based upon that one, you have to choose whether I have to, we have to make a choice that whether I have to use a mul operation or I have to use a imul multiplications. So the second one in this particular thing is that is division. So the instruction looks like this: div BL. So here the BL contains the divisor. BL. Until now we have not specified this, whether it is a multiplication part or it may be addition part. We have not specified. But in div BL, the BL part contains the divisor. BL part contains the divisor. So where dividend is stored, AL contains dividend. Because it is an 8-bit register, so we'll try to divide by AL. So division is normally done upon larger number. We'll not take any smaller number to divide. If I take a smaller number, the result may be 0 itself. So like for example, if I take 4 by 7, 4 by 7 is 0.5 and odd. So we will not divide where the answer is 0. So we generally divide bigger number by a smaller number. So if I say div BL, the number is 16 bit divided by 8 bits. So what it will be doing, it does operation upon 16 bits AX register divided by BL, and the result will be stored in AH.AL. Because if I divide 16 bit divided by an 8 bit, the maximum, that is 200 power 16 values divided by 2 power 8, the values will be 2 power 8. So it will be 8 bits only at the large. So 8 bits. So the result will be stored in AH and AL, where what is stored in AH and what is stored in AL. So generally, when I divide the two different parts, what is the thing that I will be having is, I'll be having a remainder and a quotient. So which register will get a quotient and which register will be getting a remainder. So what is important in our division? The important thing is quotient. So what is the main accumulator that we are having? An 8-bit accumulator. The 8-bit accumulator is AL. We have seen in the previous one. So the the remainder will be stored in AH register. Clear? So this is what I will be having. So in division, if I say, and another example, if I say div bx, so what it will be doing? It will be doing div. It is the moment I say bx, it is 16 bits. So bx is 16-bit divisor. So it usually does operation upon the larger number. The larger number will be stored in dx and ax accumulators. It will be divided by the bx register, and the result will be stored in dx hyphen ax, where ax gets the coefficient and dx gets the remainder. So this is all about the division part. So the next one is integer division. So the moment I say integer division, it will be I div bl. So what does it do? It is for signed numbers. It is for signed numbers. As we have seen it in the multiplication part, usually when we want to work with the signed numbers, we will go with I div instruction. That's it. So the next instruction in our arithmetic instruction is, that is CBW. It's very important because most of Viva questions come from this particular instructions. The two instructions which I want to work, which I am going to explain. That is CBW, convert byte to word, and the second instruction is convert word to double word. Word to convert word to double word. So what is why we have to convert, and what is the significance of converting byte to a word? So where it is used generally, see, for example, there may be a division you want to convert. There may be a division of an 8-bit register divided by 8-bit register. So we can do like something like, if I want to say 75 divided by 12, because this is a larger number than this one, so I can do the division part. But before doing the division part, what we will be doing, we convert this 75, which is an 8-bit register, 8-bit value to 16-bit. So how can we convert it? We'll be saying that if I take an example, if there is 37, how can we convert this? We'll convert it using a 16-bit as 0035H. In the same way, I will take one example, like there is an AL register. The AL register has 010000011, and this is in AL register. So if I want to convert this into a 16-bit, so where it have to store this one? I have to store it in AL, and second part I will be storing it in AH. So what is the value? 10000011, and Now, what is the value which is placed in AH? AH will not, as it is seen in the decimal, that is, sorry, it is 37. Okay. So, as it is seen in the decimal, so we'll say, will we place it as 000? If you place it 0, then the answer will be, we have to place all ones. Why? We have to place all ones. All ones. And the reason behind it is, we'll try to explain it. Like, we have 5. If we take a 5, this can be either plus 5 or minus 5. So if I take it as a plus 5, the value is 1001. If I take it as minus 5, this will be 1010 with the 2's complement. So I'll be getting 1011. So I'll be getting minus 5 as 1011. So it's a 2's complement representation. Am I correct? So the same, if I want to extend this particular plus 5 to 8-bit number. So what I can do, 0101, it's a plus 5. If I want to extend it to 8-bit, what I will be adding? I will be adding 0000. But if I want to extend the minus 5 as an 8-bit number, the number should be 111, because if I do the 2's complement form, what I'll be, this is, if I go with the 2's complement, I'll get this particular result. Say something like if I want to do the 2's complement form for the plus 5, what I'll be getting, look at it, 1111 1010. So add up 1. So what I will be getting, 1101 111 and 1. So it's a 2's complement of plus 5. So while doing converting, that is byte to word, we have to look whether the most significant bit value is 0 or the most significant bit value is 1. So if it is 1, if the most significant bit value is equal to 1, then I have to have infinite leading ones. That is, in a short, I can say something like that: if the number is positive, then infinite, we can have infinite leading zeros. If the number is negative, then we'll have infinite leading ones. So in a short, I can say, first we have to check out the MSB of the register MSB. If the MSB is having 1, then all the leading digits should be 1. If MSB is equal to 0, all the leading digits should be equal to 0. So for the positive numbers, the extension of the number should be zeros, and for a negative number, the extension of the number should be 1. So here, so if I want to extend the signed numbers, why to use CBW, as we already know that it is a positive number, and write the 00 and to move to the next register out of the quotient and remainder, which so we just for the positive numbers there is no need, because for all the positive numbers it will be 00 as a leading one. So if I want to add the negative numbers, if I want to extend the negative numbers, then the extension is done in the 2's complement form, so that we are using the 2's complement representation. So all the negative numbers will have a leading 1. So the next instruction we'll be having is CWD. So CWD, which is convert word to double. See, we are if you know, these are instructions where we want to have a division operation and want to have a bigger number divided by the smaller number. So it converts, that is, AX has some 16-bit number, that is 16-bit number is a word, say something like 1 0 and so on till 0 0 1, and this is stored in AX. Now if I want to convert into double word, that implies the result should be stored in DX and AX, where the values will be 0 1 0 of 16 bits, and the remaining values in DX will be 0 0 0 0 0. All 16 bits will be 0, because the most significant bit in AX register is of 0. So I can say it is a positive number. So if it is a positive number, you will have infinite leading zeros. So whatever may be the MSP, it will duplicate the number, that is zeros. Okay. The next one in our discussion of the arithmetic instruction is negate. Negate. That is NEG. Negate BL means it will negate the values available in BL register. If we give a positive number, it will transfer that number into a negative number. So what does negative give us is BL value will become 2's complement of the BL register. So it will make, if I give a value in BL, if it is a positive number, it will make a 2's complement of that particular number and will place it again in the BL register. Okay. So the next one we will be having is compare. The next instruction is compare, CMP. So what does CMP does for us? So the moment I say if I want to compare two values, what I will be taking, if there is a number like 16 and a number called 17. A comparison means what the easiest method we will be doing is we will be subtracting two different values. Like say for example, compare BL comma CL. So the easiest process is we do subtraction. So BL minus CL. We'll do BL minus CL. But the question over here is, we'll compare BL minus CL. Will the result be stored somewhere in BL or CL? No. We just want to compare the result and say which is the largest number, which is the smallest number, or whether the two numbers are equal or not. So if I say, if the result BL minus CL is positive, then we can take BL is greater than CL. If BL minus CL is equal to 0, then what I will be doing? I will be saying BL is equal to CL. If BL minus CL is a negative number, the result, that is, then BL will say BL is less than CL. So after so we already discussed, after doing the subtraction, whether this will be stored in somewhere. No, it will not be stored. So how can I check whether which is the greatest number, which is the smallest number, or whether the two values are equal or not? So for this one, we'll check the flags. After doing the comparison, we'll check the flags. So whether we'll be checking all the flags or only a few flags. See, if I'm doing BL minus CL, if I'm going with BL minus CL, there are two things which we can observe. That is, 0 may be occurring and there may be a negative number also. The moment I say there is a negative number, that implies that I'll borrow something from the other side. So when I say a borrow, then which flag will be affected up? The flag which is affected is carry flag. So from the results, we can be very sure that two flags will be affected. Those two flags are carry flag and zero flag. What are the conditions that I am having? If BL is greater than CL, if BL is equal to CL, and BL is less than CL. So if BL is equal to CL, then the zero flag will be activated, that it will be 1. If there are 3 conditions, so how many flags will be affected in general? We can say 3 means 4 combinations I can have. If I have 2 different flags, the 4 combinations are CF and with two different flags I can have 4 combinations CF and 0 flag. So if BL is equal to 0, if BL is equal to CL, then the value will be equal to 0, therefore 0 flag will be affected. If BL is greater than CL or BL is less than CL, then the 0 flag will be equal to 0 itself. Okay. Now, the other part, what we'll be discussing is if BL is greater than CL. If there are 2 numbers I can take. If 2 numbers I am subtracting from BL, a value equals CL. So if I say 24 minus 12, I will not have any borrow from that one. So what I will be getting, carry flag will be equal to 0 if BL is greater than CL. And if BL is equal to CL also, there is no carry flag because this will be 0 because borrow will not be occurring. Now the case is, now I'll do 12 minus 24. So what I'll be going, I'll borrow from this one, 2 minus 4, 12, 12 minus 4 is 8. So there is 0, 0 I cannot borrow. So I'll take a borrow from outside. So now the carry flag will be activated. So that is the case. So from this particular statement, I can clearly say, now if BL, if I say BL is less than CL, then the carry flag will be, when the carry flag will be activated or it will be set, or if BL is equal to CL, then the 0 flag will be activated. So for example, if I take something like, if compare AL with 37. Now if here the condition is, if ZF is equal to 1, then I can say AL is equal to 37. If ZF is equal to 0 and CF is equal to 0, then AL is greater than 37. Simply I can write it like, if ZF is equal to 0 and CF is equal to 1, then I can write AL is less than 37. That's it. So we'll conclude this at this particular point, and we'll come back with the 2 more very important instructions. They are the decimal adjust after addition and decimal adjust after subtractions. Thank you, and we'll be back with 2 more instructions in the next class. Thank you.